this video, let me go over a baby case for the L'Hopital's rule. So this way, we will have a better feeling about that, why the actual case has to be true, right? So why we can just differentiate the top and then differentiate the bottom and then plug in. But anyway, let me just go over the case for you guys. I want to begin with two continuous and differentiable functions. I'll just call them to be f and g. And notice I only wrote down differentiable functions because when the function is differentiable, it automatically implies that it has to be continuous. Anyway, first, I want to assume that f of a is equal to g of a is equal to 0, and we are talking about the 0 over 0 indeterminate form situation. Next, we want to have f prime and g prime to be continuous. This is going to help us to legitimately plug in a into here and here. And lastly, once again, it's going to be just for simplicity purpose. I want to have g prime of a is not equal to 0 so that I can just do this one time. But as you know, the overall case is that you can do this as many times as you need to if you see you're making the progress. But I will just do this for you guys, and in the end, I will show you guys an example. Okay, let's go ahead and do the proof. So PF for the proof. And as you can see, we are trying to prove this equality. So let me begin with the left-hand side. Let me just write down the limit as x approaching a, and then we have the function f of x over g of x. And let's see, what can we do? Here is one of the biggest key that you have to remember when you're doing proofs. You must use the assumptions, right? If you don't use assumptions, that means something is wrong for sure in your proof. So let's see. We are trying to get the derivative. We have the f prime, and we have the f of a and things like that. And especially when we are talking about the derivative, this is going to help us to plug in a into here. So we are talking about f prime of a. And we also have to know the limit definition of derivative. So let me just write it down right here as a note. Recall that f prime of a, this right here, is equal to the limit as x approaching a, and then we have f of x minus f of a over x minus a. This is just one way to define f prime of a. You can use the one with h, but this right here is more suitable in this situation. So, what can we do though? Well, here we have f of x. This is minus f of a. Can we just do that? Yes, because f of a is just 0. So when you just minus f of a, you are just minusing 0. So you are not doing anything pretty much. So this right here is equal to the limit as x approaching to a. And I'm just going to write down f of x. And I will subtract f of a on the top. Once again, this is just subtracting 0. So we are not changing the value of the original expression. And on the bottom, of course, let's write down the g of x. And you guessed it, let's go ahead and minus g of a, because this is just as equal to 0 as the other one, isn't it? Cool. And notice, I do want to divide it by x minus a so that I can call out the f prime notation, right? So beginning from here, let me divide the top and bottom by x minus a. So let me just write this down again. I will write down everything in black. The limit as x approaching a. On the top now, we have f of x minus f of a. And on the bottom, it was g of x minus g of a. And then, as I mentioned it, let's go ahead and divide the top by x minus a, because I'm trying to match the definition of the f prime. On the bottom, do the same. Right? It's just a whole fraction. We are dividing the top and bottom by the same thing. So of course, it's still the same. And then, depending on how much detail you want to show, when you have a limit right here of a quotient, it's a quotient of the limits. So let's go ahead and do that. Put this right here. So we have the limit. And then, let's go ahead and look at this. This right here, on the top, that's exactly f prime of a. So let's go ahead and do that, f prime of a. Over the bottom, of course, it's exactly the same as g prime of a. And technically, we are done. Because we know f prime and g prime are continuous, so we can just plug in. Notice though, right here, we know this is legitimate because we have the third assumption. So this right here, it's legit. And recall the definition of being continuous. If you would like, you can say this is the same as saying the limit as x approaching a. On the top, you can just say f prime of x, and on the bottom, you can just say g prime of x. Because once again, this right here is by continuous, right? By assumption number 2. The definition of continuous is that you can legitimately plug in this value into the x right here, and the limit is equal to the value. That's how it makes a continuous function. So you see, we are using condition 1 right here, and this is technically condition 3. And then this is condition 2. And then we are done. This is just a baby proof. Of course, this is also for the baby situation. So we're done. Put a box and shade it in.